Swayam Prabha. Digital India. Educated India.
Okay, so let me have your attention. Please take a notebook and write. You see, just to recap. See, if we start with if we start with an n by n matrix. See, if we start with an n by n matrix A, okay, with entries in real numbers, okay, then corresponding to that we get a linear transformation of Rn to Rn. Okay, it's a linear map. And how is it defined? The way it is defined is that you have the matrix acting on column vectors in Rn, and the action is simply matrix multiplication. You multiply the n by n matrix with this n by 1 column vector, which is whose entries are exactly the coordinates of the point, okay, whose position vector you are looking at, okay. And then here is the important thing for this matrix A. What happens is that what is the corresponding linear map? It will take the the first or the first basis vector to the first to the first column vector occurring in the matrix, and similarly it will take the ith basis vector ei to the ith column. And therefore you see the matrix is simply, if you take the corresponding linear map, okay, the columns of the matrix are precisely the images of the standard basis vectors under the linear transformation defined by that matrix, okay. So so if I start with an A here in MNR is n by the set of all n by n square matrices, okay, with R entries. Then the LA, which is the linear transformation that it defines, is simply the transformation that is going to take EI to the ith column of A, okay. And therefore you see, if you write all the columns, okay, they are each column is actually, if you take the ith column or the jth column, it is the image of the jth unit vector, okay, standard basis vector, all right. So and of course here I wanted to say that EI vector, what is this? This is just, you treat it as column vector, you put 0 0 0 except at the point at the ith position, you put 1, and all other positions you put 0, okay. So this is the standard basis vectors. And so you have this map that takes every matrix to the linear map that it defines, A going to LA, and this has also an inverse. Conversely, if you start with the linear map L, okay, if you start with the linear map L, then so let me rub this off. So if you start with the linear map L, then you can get the corresponding matrix A of L, which is simply the columns are precisely the images of the standard basis vectors, okay, that's all. And so this is a bijective correspondence, all right. And there is a little bit of maybe some bit of notational inconvenience, in the sense that I am calling the map as capital L, okay, and I am also using L on this side, okay. Here when I say the map is L, it is just something going to L of that, okay. And then in the reverse direction, it is any anything going to A of that, okay. That is a map. And maybe it's better to have used script L here, okay. And on this side, maybe instead of this A of L, I could have used script A. Then the notation would be better, all right. So if I rewrite it in that notation, then I can write. So let me write it like that, so that this map, if I call this a script L, okay, then what happens is you see L of A is L sub A, okay, and then the reverse map, if you take it in the other direction, if you call it as, so this is my script L and this is my script A, and then what happens is that this this A of L is, so if I rewrite this, it will become, this will be script A of L, okay. And then of course the fact that these two maps are inverses of each other is the following thing, namely you start with a matrix A, you apply the script L, you will get LA. Then you apply the inverse map which is script A and you will get A of LA. So I'll change this here. And the fact is that A of LA should be equal to A, okay. And similarly, if you start on the right side with the matrix L, okay, then you go to the left side by applying script A. So I'll again change this and call this a script AL. And then now if you go to the right side, you will get L of A of L, and that has to be equal to L. And by the way, this is script L of A of L, okay. So these two are inverse, maps to each other. So in other words, there is a way of looking at every matrix as uniquely as a linear map and conversely, okay. Now with this background, we want to, so we have, therefore you have this map here. So oops, so I have this map here. So again, let me just change the notation. So this is script L, okay. And mind you, there is also a map in this direction which is script A, which is L inverse, all right. Now for, so I should change, so I should write a few more things. So this should be L of A, and this thing on the right side should be script A of A, okay. Now you see, what we are interested in is rigid motions, and therefore we are looking at isometries. And then the question is, the isometries, general isometries are not linear, but an isometry is linear if and only if it takes origin to the origin, okay. So you get these linear isometries which preserve the origin, so that's what this subscript 0 means, okay. And then these are all linear maps, and these linear isometries is sitting inside as a subset, okay, of all the linear maps, okay. Linear isometries are special linear maps which preserve the dot product, okay. Now therefore what happens is that anything on the linear map side corresponds to a matrix on the matrix side. So if you take a linear isometry, then it should correspond to certain matrices. What are those matrices? That is the question, and the answer is the matrices are the so-called orthogonal group, okay. And why is this happening? This is what we would like to understand. So you would like to understand that if you take a linear isometry, then its matrix is a member of the orthogonal group, namely it satisfies this condition, transpose A is equal to identity, okay. So this is what we want to understand. Now for that, what I am going to do is I am going to try to understand what this meaning of linear isometry is actually. It is, I am just trying to recall a lemma that we proved, that an isometry is linear is the same as saying that the isometry preserves the origin, okay. And that is the same as saying that it is simply a map Rn to Rn which preserves dot product. So if you want to say it in one word, a dot product preserving map has to be an isometry, it has to be linear, it has to take 0 to 0, and it will be an isomorphism by linear algebra, okay. So so let us do this. So here is a very, very simple lemma, and this lemma uses a little bit of linear algebra, but I'll tell you what is the linear algebra that is involved. So the lemma is the following. Suppose H is suppose H, so I'll call H as so H is a linear map from Rn to Rn, okay. Then H preserves dot products, okay, if and only if, okay, H EI dot h ej is equal to ei dot ej for every I comma j, all right, where the ei are the standard basis vectors e1 dot dot dot. So when I say for all I comma j, I mean 1 less than or equal to I comma j less than or equal to n. Okay, so so where e1 etc. up to en are the standard basis column vectors. So you see, therefore you see this e1 is therefore 1 0 0 0, e2 is going to be 0 1 0, etc. And en is going to be just uh, 0 dot 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 0 1. Okay, so so here is the statement. So the statement is, so what is the proof of this? See, the proof of this is that the first thing is I am taking a linear map from Rn to Rn. In fact, I don't even need to take linear map from Rn to Rn, but the point is that we have already seen any map from Rn to Rn that preserves dot product has to be linear. Okay, so I don't, that it preserves dot products is the most important condition. Okay, so you see, the first thing is so we have to prove two ways. Okay, preserving the dot product means that it preserves the dot product only for the standard basis vectors. Okay, and conversely, and why this is being done is because you see this thing on the right has a very nice expression. It is Kronecker delta ij. You see ei dot ej, okay, mind you, all the eis, every ei is a unit vector because it has only one entry which is 1. Okay, therefore the sum of the squares of the entries is going to be 1, and that is the norm square. So norm squared is 1, so the norm is 1. For every ei has norm 1. Okay, also if you take a dot product with an ei with a different ej, okay, then you see you are going to get 0. Okay, because you see if you take ei is just going to be 0 0 0 with in the ith place. I mean, you're in the ith position. I'm going to put a 1 there, and then the rest of it is all 0. Okay, so this 1 is in the ith position, and then if I take ej similarly, this is going to be 0 0 0, and then I'm going to have 1 in the jth position. Okay, and then all zeros. Okay, what is ei dot ej? How do you write this ei dot ej as a dot product? See, if you want to write it in terms of column vectors, okay, basically you have to take the corresponding entries in ei and multiply with the corresponding entry in ej, and then you have to add up. But you can see this as matrix multiplication. If you see this as matrix multiplication, this is actually, if you write it, if you think of ei as a matrix, this is actually transpose ei dot ej. You can write it like this. Okay, now I will remove the I will remove the dot. See, if you see it as dot product, it's ei dot ej. But if you see it as matrix multiplication, it's just transpose ei ej. Because you see, what is transpose ei? Transpose ei is going to be, I'm going to get 0 0 0 1 0 0 0. Okay, and here is the 1 in the ith position, and this is what transpose ei is, and ej is going to be like this. So it will be 0 0 0, then I'll have a 1 in the jth position, and then rest of it is all zeros. Okay, and multiplying these two will give you delta ij. Okay, more generally, what am I saying? I'm saying more generally we have you can see the dot product of two vectors as matrix multiplication. So more generally we have v1 dot v2, okay, is transpose v1 v2 as matrices. Okay, because you see, if you take v1 as sigma lambda I equal to 1 to n, okay, that means v1 is the column vector given by lambda 1 etc. up to lambda n. That's what it means, right? And mind you, this lambda 1 up to lambda n is, if you write it in vector notation, it is summation, you know, if you want I equal to 1 to n, you know, I can put 0, 0, 0 everywhere and just lambda I in the ith position. Okay, and this can be written as summation I equal to 1 to n. I can pull the lambda I out, and what I will get is 0. So this lambda I is in the ith position, 0, 0, 0, 1 in the ith position. Okay, but this is exactly ei. So this is sigma, you know, I equal to 1 to n lambda I ei. Okay, so you see the column vector for this is exactly this. Okay, and similarly, if you write v2 as sigma, you know, I equal to 1 to n mu I ei. Okay, then what is v1 dot v2? v1 dot v2 will be just summation I equal to 1 to n lambda I mu I. That is a dot product. Okay, but how will you see it as multiplication of matrices? You can also take transpose v1 and simply multiply by v2, because transpose v1 will give you transpose of this. So you will get, you know, lambda 1 etc. up to lambda n. This is transpose v1. You multiply it with v2, which is just mu 1 etc. up to mu n, and of course you are going to get you know, sigma, again sigma lambda I mu I equal to 1 to n. So the point is, how do you connect the dot product with multiplication of matrices? The dot product of two column vectors is, you simply take the transpose of one column vector and multiply it with the other vector. Therefore, so you see, this is just a translation from, you know, dot product of vectors into matrix notation. Okay, that's what I wanted to understand. So if you look at it like that, okay, so now you see, so I want to say that suppose H from Rn to Rn, you know, preserves dot products. That is, you know, it means that, you know, H of V1 dot H of V2 is equal to V1 dot V2. Suppose this is true. Then we have already seen, see, if this happens, then H has to take 0 to 0 and H will be linear and H will be an isomorphism. We have already seen that. Okay, then as we have seen, H 0 equal to 0, H preserves norms. See, in fact, the truth is, first H preserves norms, therefore H of 0 is equal to 0. Okay, and H is linear, H is a linear isomorphism. Okay, now, but what I want you to understand is that if this is true for all V1 and V2 in Rn, then of course it is true for any Ei Ej also. So then of course, clearly, as a special case, H of Ei dot H of Ej will be Ei dot Ej for all I comma j. Okay, and mind you, this is of course delta Ij by definition, where delta Ij is the Kronecker delta Ij. Delta Ij is 1 only when I is equal to j, otherwise it's 0. So delta Ij is the Kronecker delta. So this is 1 if and only if I equal to j, it is 0 otherwise. Okay, so if H preserves dot product, then Hei dot Hej is going to be Ei dot Ej is equal to delta Ij, and we have to prove the converse. Conversely, suppose Hei dot Hej is equal to Ei dot Ej, okay, then you know, H has to preserve dot products. Okay, and that is what this involves is, it involves this important fact that you see these Eis form a basis. Okay, that's the whole point. Okay, so conversely, suppose H is linear and H of Ei dot H of Ej is equal to Ei dot Ej is equal to delta Ij for all I comma j. Of course, when I say for all I comma j, it's understood that 1 less than or equal to I comma j less than or equal to n. So, okay, suppose this is true, then the claim is HV1 dot HV2 is V1 dot V2 for all V1 and V2. Okay, so then we can show that H preserves dot products. So you calculate HV1 dot HV2. Okay. Now here is the important thing. You see, the fact is that any vector can be written in terms of the EIs. That's the whole point, with unique coefficients, because the EIs form a basis. So this HV1 will become H of, so V1 can be written as sigma lambda EI, I equal to 1 to n, and these lambda i's are unique for the vector V1. Okay, and why is this? This is because E1 etc. up to En form a basis. For Rn over R. Okay, what is the property of a basis? Any vector can be written as linear combination of the basis vectors, and the coefficients in the linear combination are unique. That is the universal property of a basis. So you can write like this, and you will get dot H of summation I equal to 1 to n mu I EI. You will get it for the other vector. So this is for so by the way, this expression is for V1, this expression is for V2. Okay, and now you see, you use the fact that H is linear. Okay, so H is linear means it will distribute over sums, and it will respect scalars. Scalars can be pulled out of H. So this term will become summation I equal to 1 to n lambda I H EI. Okay, that is the first term. That's because of linearity. Okay, H distributes over sums. H of V1 plus V2 is HV1 plus HV2, and then H of lambda V is lambda HV. That's because H is linear. Okay, so I'm using the linearity of H, and this second term is going to be similarly dot. There's a dot in the middle. Summation I equal to 1 to n mu I H of EJ. So H of EI. Okay, and you see now the dot product is distributive, and scalars can be pulled out. So this expression will become double summation. So just to make the summation, because I don't want to use the same index in both, I will change in the second one, I will make it j. Okay, so I will put j here. All right, and then I'll write double summation I equal to 1 to n, j equal to 1 to n, and what I will get is I'll get lambda I lambda j, lambda I mu j rather, lambda I mu j, and what I will get inside is HEI dot HEJ. This is because of the fact that the dot product is distributive over sums, and in the dot product you can pull scalars out. Okay, so you can write it like this, but you see, what have you assumed? You have assumed HEI dot HEJ is EI dot EJ, okay, which is delta IJ. All right, therefore you see this quantity is actually delta IJ by assumption, and delta IJ survives only when by the way, sorry, the thing outside should be j here. Okay, this delta IJ survives only when I equal to j. So basically this will sum out to I equal to 1 to n lambda I mu I, which is the V1 dot V2. So you see, HV1 dot HV2 will be V1 dot V2. So the moral of the story is the following: if you have a linear map, to check that it preserves the dot product for of any arbitrary two vectors, it's enough to check that it preserves the dot products only for the standard basis vectors. Okay, but now this is exactly, so this is the end of the proof of this claim. Okay, now this exactly tells you that the matrix of such a map has to be an orthogonal matrix. Okay, so now here is the claim. The claim is, H is a linear isometry if and only if the matrix of H, that is, in our notation script A of H, okay, is an orthogonal matrix. No, I think in the lemma, I think I did say H is linear. Did I say that? So I have done that. Yeah. So one has to be a little bit careful, because if it is not linear, then that means the only problem is 0 will not go to 0. If 0 doesn't go to 0, I cannot distribute over sums and scalars and all that. There will always be a minus h0 sticking everywhere. Okay, that's all. Yeah, it's correct. You have to be very careful. You have to just notice that. So linearity I need. One direction I don't need. Other direction I need linearity. Is that fine? Can I go ahead? I am just using the fact that v1 dot v2 plus v3 is v1 dot v2 plus v1 dot v3. Okay, the dot product distributes over sums on both both arguments, and from each argument a scalar can be pulled out of the dot product. I am just using that. Mathematically we say that the dot product is what is called a bilinear form. That is, it is dot product takes two arguments, so it's linear in each of the arguments, so it's called bilinear, and in each argument you can pull out a scalar. So dot products are called bilinear forms. So so these are there is a very general theory called the theory of bilinear forms, and the important thing is that here you are looking at these are symmetric bilinear forms. Okay, therefore they are connected with they are orthogonal. Here in this case they are actually orthogonal matrices, but more generally you can study similarly skew symmetric, Hermitian, and so on bilinear forms, positive definite. So there is a whole study of bilinear forms of which this is a very special case. This is a positive definite symmetric bilinear form. Okay. Yeah. That's right. No, that's something that we have already done. We have already proved that H preserves the norm. That's, see, remember, it's very, very easy to understand. See, if H preserves the dot product by HV1 dot HV2 is V1 dot V2, you put V2 equal to V1. You will get HV1 dot HV1 is equal to V1 dot V1. But HV1 dot HV1 is just norm HV1 squared. And V1 dot V1 on the right side is norm V1 squared. So you are getting norm HV1 squared is equal to norm V1 squared. If you take square roots, positive square roots, you will get norm HV1 is equal to norm V1. So therefore H will preserve norms. And if you put V1 equal to 0, you will get norm H0 is equal to norm 0, which is 0. And that will force H0 equal to 0. So it will fix the origin. And once it fixes the origin, we have already proved it is actually linear. Okay. So one way of the lemma, you don't need to already assume that H is linear. It's enough to assume H is just dot product preserving. That will force it to be linear, a linear isometry. The other direction, you have to assume H is linear, because things may go wrong if H doesn't take 0 to 0. Okay, that's what you have to notice. Now you see, yeah, no, I'm not saying every linear map preserves the norm. No, we are only looking at those which preserve the dot product. The key is in a nutshell, remember that it preserves dot product. That kind of gives you everything else. The preserving the dot product makes it preserve the norm. It makes 0 to go to 0. It makes it an isometry. It preserves angles. Okay, and it preserves, of course, dot products. Then it is isomorphic. That means it is actually bijective. That is because of linear algebra. You get all this from that. So this preserving the dot product is a very, very important condition. It has several ramifications. Okay. So let us come to this claim. You take the linear isometry. What is the speciality of the matrix that represents it? It has to be an orthogonal matrix. That is, if script A of H is capital A, then transpose A is equal to identity, where this identity n by n is just the n by n identity matrix, which is by definition it is a matrix which is 1 on the diagonal, 0 everywhere else. So this is this is n by n matrix. I put 1 1 1 1 here, and then I put 0 everywhere else. This is what. Okay. So what is the proof of this? The proof of this is very, very easy. So the proof is a very, very simple thing. Notice that for any matrix, let us say B equal to Bij, okay, we have, suppose I write transpose Ei, okay, B Ej. Okay, if you write this, you will simply get Bij. It will pick out the Bij. Okay, why is this true? Because you see, if you so look at this, what is Bij? Bij will be, you're going to put this B entries here, and then you're going to put Ej here. Okay, and Ej is what? 0, 0, 0, 1 only in the jth position. Okay, now when you multiply this, every row when you multiply, only the jth column, only the entry in the jth column will survive, because in the product, when you write the product, what will happen is that you are going to get only you have to, when you multiply by a row, you see you are multiplying this row with this column, and only the jth column entries will survive. Therefore the effect of this is that you will only get the jth column of B. Okay, so this will be jth column of B. So and which is all these things I have put a star. Okay, and this is, if you want, CJB, this is the jth column of B. Okay, and now if you take the jth column of B, and then I have to pre-multiply by this transpose EI. Okay, so therefore transpose EI BEJ. Okay, mind you, matrix multiplication is associative, I can do it in any order. So this will be equal to transpose EI multiplied with this CJB. Okay, and what is that going to be? This is, what is transpose EI? It is 0, 0, 0, 0, 1 in the ith position, again 0, 0, 0. I am going to multiply it with the jth column of B. It's going to be B first row jth column, B second row jth column, blah blah blah, B nth row jth column, and the only entry that is going to survive here is going to be Bij. When you multiply this, you will simply get Bij. Okay, therefore moral of the story is, for any matrix B, if you pre-multiply by transpose EI and post multiply by Ej, it will pick out the ijth entry. All right, now just use this. So if H is a linear isometry, okay, then and only then, as we have proved, the matrix of H, the matrix of H. So I will say that. So let me say the following. So what did we prove? It's H is a linear isometry if and only if it preserves the dot product for the EI Ej. So HEI dot HEJ is equal to EI dot EJ is equal to delta Ij for all I comma j. Okay, but you see, translate all this into matrix language now. Okay, if you translate it into matrix language, so translate it into matrix language, in matrix multiplication language, this what is the see, when you take two vectors and multiply them, the result is you take transpose of the first vector and simply multiply with the second vector. So this guy here will be transpose EI into EJ. That's what it is. And this is, and mind you, I am not putting anything in between. It's just matrix multiplication, and this is going to be, of course, delta Ij. Okay, in the same way, you see, when you HEI is a vector, HEJ is another vector. Okay, then what is this going to be? This is going to be transpose HEI into HEJ. So this is just going to be transpose HEI into HEJ. Okay, but just think about this. You see, so I want to say, what do I want to say? But look at this. See, when you say script A of H is A, is Aij. Okay, what does it mean? You are saying the matrix related to associated to the transformation H is A. What is a matrix associated to a transformation? The columns are exactly the images of the standard basis. So you get this result, namely that H is a linear isometry if and only if the matrix associated to H is orthogonal. Okay. Okay. So yeah, so let me again say this in the following way. See, HEI dot HEJ is equal to EI dot EJ is equal to delta Ij. If you write it like this, if you write it in matrix form, this is A into EI, A acting on EI, and then dot A on EJ. Okay, but you see dot product of these two is the same as taking the transpose of the first and multiplying by the second. Okay, so this is going to be, so I will remove this dot in the center. Okay, and I will convert it to matrix multiplication. It will become transpose this into this. Okay, and this is equal to delta Ij. Okay, but you see you have this property transpose AB, transpose of AB is transpose B transpose A. Okay, therefore what will happen is that this will become transpose EI transpose A into EJ is equal to delta Ij. But you see, we just now said this. If you pre-multiply by transpose EI and post-multiply by EJ, you will pick up the ijth element. So what this tells you is that transpose AAA, the Ij element is delta Ij. That means transpose AA is identity map. Okay, is the identity matrix. Okay, only the identity matrix has entries delta Ij. Okay, so this is if and only if transpose AA is equal to identity. Okay, so this is another way to see it. I mean, this is just manipulation with translate from vectors to matrices, and then remember use all known properties of for example here transpose of a product is product of the transposes in the reverse order. All right, you use that. Now see, the moral of the story is that there's something else that has come inside now. You see, so therefore we have that all the linear isometries, they are just members of the orthogonal group. Okay, now there is something that extra that needs to be understood. The first thing is that the members of the orthogonal group, they are not just matrices, they are actually invertible. Okay, so there is a subgroup, there is a bigger group sitting in between, which is called the general linear group. Okay, which is the set of all invertible linear transformations. So I will just upgrade this diagram. I wrote this diagram. You have M and R, two on this side linear R linear maps from Rn to Rn, Rn to Rn. Okay, you had this L, and this is just A going to script L of A is L sub A. Okay, this is a, mind you, this is a bijection. Okay, this is a bijective map. All right, and it has an inverse. The fact is that here there is the there are the linear isometries. There are linear isometries Rn to Rn, which are the same as isometries from Rn to Rn that fix 0. Okay, and under this map, this corresponds to the orthogonal group. That's what we have proved. But what is going to come in between is, here you are going to get automorphisms of R from Rn to Rn. And what is this? So automorphisms are self isomorphisms. Okay, auto means self. All right, so automorphisms are self isomorphisms. So, and what are the self isomorphisms? These are the invertible linear maps. So these are the self isomorphisms or invertible linear maps. Okay, and you see, if you so you see the all linear maps need not be invertible, only some of them are invertible, and the condition for invertibility is that if you write the matrix for the corresponding map, that matrix must be invertible, and that is equivalent to saying that the determinant of that matrix is not zero. Okay, so if to check that a map is invertible, you write its matrix, okay, and you check that its determinant is not zero. So what happens is that on this side, this will correspond to this, what is called as general linear group. GLN R are the invertible matrices. So on this side, Mn is all matrices, GLN is invertible matrices, and these are essentially the matrices with determinant not zero. A matrix is, square matrix is invertible if and only if its determinant is not zero. So this is something that you study in linear algebra. Okay, so the point is that every member of the orthogonal group is actually invertible. And of course you know that, that's because you see the members of the orthogonal group are correspond to linear isometries, and we proved this last time that linear isometries are all isomorphisms. Okay, a linear isometry is injective a linear map from the same dimension space to the same dimension space, and because of the rank nullity theorem, an injective map from this linear map from the same dimension space to the same dimension space is the same as a surjective linear map from the same dimension space to the same dimension space, and they are both the same as linear isomorphisms. And linear isomorphisms, if you represent them by matrices, the matrices must be invertible. So this orthogonal group matrices must be invertible. Another way to see it is, what is orthogonal group? It is the set of all A in MnR such that, so the condition is transpose A is equal to identity. Right? So, but you just look at this condition. You apply determinant to it. See, if you apply determinant to it, you know this thing, the determinant of AB is determinant A, determinant B. Okay, determinant of a product of two matrices is the product of the determinants. Okay, determinant is, we say that determinant is a homomorphism into real numbers. Okay, that is, it preserves product. You take two matrices, take the product and then take the determinant. That will be the same as first taking the determinants and then taking the product of the determinants. The product of the determinants of two matrices is the same as the determinant of the product. Okay, therefore if you apply determinant to this, on left side you will get determinant transpose A into determinant A is equal to determinant of identity. But determinant of the identity is 1, and determinant of a matrix is the same as determinant of its transpose. If you transpose a matrix, its determinant does not change. So the left side is going to be determinant A squared. Okay, so from this you will get the determinant A, okay, is plus or minus 1 for every A in the orthogonal group. So this is a very, very important thing. Okay, the members of the orthogonal group, they will have determinant 1 or determinant minus 1. Okay, and in particular determinant is not 0. Okay, therefore they are all invertible. Okay, so what you must understand is that on this side you have all the linear maps. Inside that you have the invertible linear maps, and inside that you have the linear isometries. Okay, and correspondingly on the right side you have all the matrices. Inside the matrices you have the invertible matrices, which is called the general linear group, GLN, and inside the general linear group you have the orthogonal group. Okay, and the beauty is that orthogonal matrices, determinant will always be plus or minus 1. Okay, whereas if you take a general linear group element, a general invertible matrix, determinant will be only a plus or minus a non-zero quantity. It need not be plus or minus 1. It will be not 0, so it will be a plus or a minus of a positive real number. All right. Now, so there is only one more thing that you have to notice to go to rigid motions. Okay, rigid motions, we want to understand rigid motions. We realize that rigid motions are isometries, and but all isometries are not rigid motions. there's one extra thing about rigid motions, and that is that the rigid motions also preserve orientation. Okay, so the question is, what more should you add to an isometry so that it becomes a rigid motion? The obvious thing is that you have to add preservation of orientation, and this preservation of orientation is exactly what gives the plus or minus 1 sign. Okay, so what happens is that if you take the elements of the orthogonal group which have plus 1 sign for the determinant, okay, these are going to be precisely the rigid motions. Okay, so therefore we have finally this statement that the group of rigid motions are exactly those orthogonal group elements with determinant 1, and this is given a special name. It's called special orthogonal group. Okay, all right. Whenever determinant is 1, such elements are called special. So even in GLN, if you take the elements of GLN with determinant 1, it's called special linear group and it is called SLN. Okay, and similarly in the orthogonal group, if you take elements of determinant 1, it's called special orthogonal group, and it will be intersection of the orthogonal group with SLN, and it's called SON. And the point is that this SON is the final group that we want. This SON, which is a special orthogonal group, they are exactly our rigid motions. Okay, so that is the the final aim of this whole discussion. Okay, so then the next thing that we need to do is we have to first make the following statement, namely you take a curve, move it by a rigid motion. Okay, but now moving it by a rigid motion means that you are only taking an orthogonal group element with determinant 1. So you can actually write it using matrices. And then what we can verify the following statement, that if you take a curve and move it by a rigid motion, then its curvature and torsion will not change. Okay, now using the Frohne-Serre differential equation relations and this description of rigid motions as the special orthogonal group, you can verify the statement that if you take a curve and move it by a rigid motion, the curvature and torsion functions will not change. Okay, so that is the first part of the classification theorem for curves. Okay, so that's what we will do next. All right, so I'll stop here.